Yeah, dear students, in the previous discussion we have studied about the crystal field splitting and also crystal field theory of the octahedral complexes. Having said about the crystal field theory of the octahedral complexes, it becomes important for us to study about the crystal field stabilization energy. Before I say what is this crystal field stabilization energy or I define it, let us move on to some other discussion here. When we have told that in the octahedral complexes, the degenerate d orbitals are split into two levels, say T2g and Eg, then when we say that the first electron is entering into the octahedral complex and that electron will ever prefer to move to the lower energy T2g level. That is to say that T2g is of lowest energy, hence electrons must prefer the lowest energy orbital so that the total system becomes of lower energy or its energy decreases, and we could say when the energy of the total system is less, then that complex or that compound is more stable, and this is how it is defined for the stability. And hence when the electron now tries to move to the T2g level, then it gets stabilized, or to say that it can stabilize up to minus 0.4 delta O, or it is up to 4 dq, minus 4 dq, or we can say that 0 minus 0.4 and up to it is plus 0.4 delta O, and similarly it is plus 4 dq, and this is how it gets stabilized. And hence in the T2g we have three orbitals dxy, dyz and dzx. And whenever they are getting into these three orbitals, there is an option, it's called as they are again degenerate, and hence electron can be accommodated in either dxy, dyz or dzx. Of course, the degeneracy will be lost as the number of electrons do increase here. And hence, as I told, whenever the electrons do get into the T2g, they are getting more stable by either 4 dq value or 0.4 delta O value. Hence, we can define what is crystal field stabilization energy. Coming to the definition, we could say it is lowering in the energy of the central metal ion in a given ligand environment. In the sense, it can be a tetrahedral ligand environment, or it could be octahedral ligand environment, or it can also be a tetragonal and square planar complexes or square planar ligand environment. And hence, when the metal ion finds a lowering in the energy in the given set of the ligand orbital due to the crystal field effect, could define what is crystal field stabilization energy. To define it fully, we can say it is a lowering in the energy of the transition metal ion in a given ligand environment due to the crystal field effect, and hence this is called as crystal field stabilization energy. And hence stabilization energy is now concerned about lowering in the energy of the central metal ion, and when it could happen in the presence of the given ligand environment, whatever it could be, due to what? And due to crystal field effect. Hence lowering energy is observed, and this could define the crystal field stabilization energy. And coming to the octahedral complexes, we can have a calculation of crystal field stabilization energy over here. And crystal field stabilization energy could be calculated in either in terms of dq value or in terms of delta O value, and hence it is equal to minus 0.4 into n of T2g. N is number of electrons present in the T2g plus 0.6 into n of Eg. N is referring to the number of electrons which are present in the Eg orbital. And finally, we get the CFSE here, and we can neglect the negative sign here. Now coming to the first electron which enters the T2g, we call that as a D1 system. So in the D1 system, obviously it goes to any one of the T2g orbitals, and in that it will be stabilized by 0.4 delta O or by 4 dq value, and therefore this is the stabilization energy given for the D1. Similarly, we can calculate it for the D2 as well as the D3 metal ions. Coming to D2 and D3, it is easier for us to calculate because we just have a number of electrons in T2g, where these 3 electrons or 2 electrons or 1 electron can be considered in T2g, hence its energy is given by multiplying the number of electrons with the crystal field splitting energy of T2g, that is all. But when it comes to the D4 system, where we have 4 electrons present, now there will be an ambiguity. What is it? It is that now the fourth electron, either it can get into the T2G by the way, it getting paired up with the one of the orbitals. In the sense, electrons do get paired up here in one of the orbitals, or there is another chance given to that, in the sense that fourth electron may get into higher energy EG level. So, either it is getting paired up in the T2G or it is moving on to the EG. So, we will be calculating the CFSE based on these two conditions. Now, these two conditions will give rise to two set of complexes, and we call that as high spin complex as well as the low spin complex based on the high spin condition or based on the low spin condition. Now, let us consider the high spin complexes or high spin condition. What is it? Let us today. Say here, when the fourth electron gets into the EG level, what we have is the singly occupied T2G orbital and singly occupied EG orbital is one of the EG orbitals, maybe dx square y square or dz square based on the possibility. So, now what we have is the number of unpaired electrons, it is more here, because the reason I will provide you here, number of unpaired electrons do increase in the high spin condition. Let us see why the high spin condition is observed. In the high spin condition, what we observe is the crystal field splitting energy is less than that of pairing energy. So, the electrons rather than getting paired up in the lower energy T2G level, they prefer to move on to the higher energy EG level, because the crystal field splitting energy and the gap between T2G and EG is very much less now, and hence the fourth electron is getting into the higher energy EG level. Now, what could happen over here is that since the gap is less, the fourth electron is in EG. As a result, high spin condition is observed, and usually high spin condition is observed by the ligands which are weak, and hence the complex is also called as weak field complex. Coming to the next one, what is the weak high spin, not the high spin, it is strong field complex, or we can also consider it as the low spin condition. In the low spin condition or in the strong field complex, what could happen is the fourth electron, rather than getting into the higher energy EG level, it gets paired up in one of the T2G orbitals with the electron. The reason here is that here pairing energy is lesser, or we can say crystal field stabilization energy is more than the pairing energy. Because of the lesser pairing energy, now the electrons do prefer to get into a paired state. The pair up of electrons do take place. Now, what would happen? Number of unpaired electrons do decrease here, and hence in the strong field complex, or we can say in the low spin condition, electrons first prefer to be paired up in the lower energy level, and once all these orbitals are paired up, then the next electron may move on to EG level. And this condition could be observed when the ligand is a strong ligand, and hence the complex is also called as the strong field complex. So, based on high spin condition as well as the low spin condition, we will have to calculate the crystal field stabilization energy, and it is applicable to tetrahedral, octahedral, square planar and tetragonal complexes. Thank you.